We present a robust and general solution for learning manipulation policy that enables the singulation and grasping of thin, deformable objects, incorporating embodied multisensory integration. The learned manipulation policy successfully handles a variety of challenging deformable objects across multiple environmental conditions. The robot was driven by the same learned policy for all deployments. It conquered suit fabrics, different textures of paper, hotel towels, difficult hybrid materials, and many more, which pose great challenges for perception and manipulation, with exceptional robustness. Here is how it works. The robot first proactively interacts with the object via a slip module to obtain rich multisensory information. Within the module, the object mask derived from segment anything model is rotated at various angles and fed into a fully convolutional network to infer pixel-wise affordance maps. The pixel with the highest value is selected. Its position identifies the slip point, while the gripper rotation corresponding to its affordance map determines the slip direction. The robot then performs the slip motion to interact with the object. Multisensory observations are obtained, including vision, touch, and muscle proprioception, containing insights into unobservable physical characteristics. Using base encoders, each observation is transformed into unified feature vectors. We introduce an attention-based multisensory encoder for effectively integrating features of multisensory observations. Touch features from the thumb and index finger are synergistically integrated, using a cross-attention mechanism for enhanced touch feature fusion. Through subsequent self-attention mechanism, features from different senses are effectively converged into a latent vector for mapping action. To enhance our learning efficiency and performance, we introduce a hierarchical, dual-loop policy structure. The outer loop policy outputs to select between two distinct action spaces, coarse and fine. The fine action space covers a smaller range but benefits from dense discretization, whereas the coarse action space enables broader movements with sparse discretization. Using the same multisensory encoder, the inner loop policy maps observations to a concrete action within the selected action space, which the robot then executes. We train the manipulation policy with reinforcement learning in the real world. Our setup features two robot arms, each equipped with an RGBD camera, a force-torque sensor, a soft gripper, and the fingertips of the index and thumb are equipped with vision-based tactile sensors. Robots explore and learn policy simultaneously in two parallel environments, and update policies based on received rewards. In the fabric environment, rewards come from matching QR code data to a preset sequence in the manufacturer's database. In the book environment, rewards are determined by changes in page numbers. We integrate automated recycling mechanisms to reset the environment, reducing the need for human intervention. With the proposed methodology and mechanisms, the manipulation policy was learned in just 6 hours. Our experiments demonstrate that the learned policy is able to successfully present fabric options, layer by layer, much like a salesperson in a suit shop. Or turn the pages of a book assembled by printer paper, from the beginning to the end, accurately and consistently, without a single failure. To evaluate robustness and generalization, we tested the learned policy under various conditions and with different object materials that were never encountered during training. The learned policy successfully generalized to manipulate various textures of paper, suit fabrics, and other daily objects. The generalization of our learned policy was further validated with objects made of hybrid materials, such as a fabric booklet in which each fabric sample is separated by a piece of paper detailing its specifications, and a culinary setting where a robot sequentially picked up baking paper and spring pancakes. The reliability of our policy was further validated through tests conducted at various tilt angles of the workspace. As the workspace's tilt angle increases, the physical interactions between layers change due to shifts in the direction of gravity, subsequently affecting object manipulation. Nevertheless, our approach consistently demonstrated its zero-shot generalizability across these conditions. Here, we showcase the slip module's robust generalization across varied object positions and orientations. Our work opens new frontiers in the manipulation of deformable objects, representing a significant step toward achieving human-level sensoromotor intelligence in robotics. The learned policy, with embodied multisensory integration, could enhance applications ranging from factories to homes. Thanks for watching.